Now, what do we need to do to find? First of all, what's going on in this system? Let's figure this out. I have an infinite wire. So, if there is current running through that wire, what would this cause? It would create a magnetic field circling the wire. This magnetic field circling the wire will pass through the loop here, which means there will be a flux through that loop. First part of the question asks me to find the mutual inductance. How did we define mutual inductance? Mutual inductance was very simple. The flux through the loop will be proportional to the current through the wire, and the proportionality constant was the mutual inductance. Basically, that's asking that, right? So, how am I going to calculate mutual inductance? First, I need to calculate the magnetic field created by the wire. Then, integrate this to find the total flux through the loop, which will give me the mutual inductance. But after that, find the current that runs through the loop as a function of time. Why is there a current running through the loop? Because the current in the wire is changing with time, which means the flux through the loop is changing with time, which means there must be a current, induced current in that loop. Okay? And finally, find the total force the wire applies to the loop. And why is that? Because the wire is creating a magnetic field, that magnetic field will act a force on the induced current in the loop. Right? So now that we know physically what happens in the system, let's quickly calculate everything that's asked. Okay? First, if I am at a distance r away from my wire, how do I calculate the magnetic field created there? The magnetic field created there is best calculated using Ampere's law. Great. Integral B dot dl is mu 0 I in, which is exactly I wire. So this is going to be 2 pi r times B magnitude is mu 0 I wire. So if I'm at distance r away from my wire, the magnitude of the magnetic field is mu 0 I wire divided by 2 pi r. That's great. But now that I've actually calculated the magnetic field, I want to calculate the flux. What's our definition of flux? Flux through a constant for a constant magnetic field and constant or straight rectangular area was A dot B, right? But can I use that now? No, I cannot. Why? B is changing at each point inside the loop. So what do I need to do? I need to actually integrate B dot dA. Essentially, what I need to do is to take small sections where magnetic field is constant and calculate the flux, small flux through that section. Let's say the distance here is x and the thickness of this small section is dx. Can you tell me what's the small flux through that section? Now magnetic field is constant in the small area, so I can use its value mu 0 I divided by 2 pi x, right, times the area of that section, which is going to be L times dx. So now I'll write this as integral d phi, which I'll write as mu 0 I divided by 2 pi x L dx. What are the limits on my integration. X starts at D and goes all the way to D plus L. Excellent. So apparently the flux through the loop is, I'm taking the constants out, mu 0 I L over 2 pi integral 1 over x from D to D plus L dx. What's the integral of 1 over x? ln. Great, natural logarithm. Mu 0 I L over 2 pi. It's going to be ln D plus L minus ln D, which I'll actually just write as ln A minus ln B is ln A over B. So that's how I'm going to write this. So now, can you tell me from this formula what's the mutual inductance between the wire and the loop? Yes, you can. It's everything except the current here, right? So mutual inductance is apparently mu 0 L over 2 pi ln L plus D divided by D. All right? Good, good. Now, so we've done part A. Find the current that runs through the loop as a function of time. Clearly indicate whether the current is clockwise or counterclockwise. Okay, that's great. We can, I think, do it without even writing anything. Okay, let's try to do it on the screen here. Which way is the magnetic field created by the wire? Is it into the loop or out of the loop? Into the loop. So great. The magnetic field here is into the loop. Is that magnetic field increasing or decreasing with time? It's decreasing. Why is it decreasing? Because my current is exponentially decreasing with time. Magnetic field is also decreasing. If the total flux is decreasing, what should be the direction of the magnetic field created by the loop? It should be in the same direction. It doesn't want the flux to decrease. So the magnetic field created by the current in the loop should also be into the loop, into the screen, right? Which means the current is going clockwise, okay? Maybe, okay, I'm pretty sure that's the correct answer, but let's write this down, okay? I'm going to say, this is I wire, and this is the loop. I wire is decreasing with time. B is, or B created by wire is into the page within the loop, which means flux of the loop is decreasing with time. Okay. Then B loop is in the same direction as B wire, which means it must be into the loop. So I loop, to create something into the wire, must be clockwise. Okay? Good. Now, by just looking at the system, can you also answer part C? Is the wire pulling or pushing the loop? I mean, that sounds very 50-50. So how many of you say it's pulling the loop? How many of you say it's pushing the loop? How many of you are not expressing any opinion? Okay, now, come on, you're college students right now. You should express your opinions, even when not asked. So that's a terrible joke, but at least one person laughs, so it's not too bad. Now, if I had two currents in the same direction, did they pull each other or push each other? they pulled. Now, here, what kind of forces will there be? Well, I know that the forces will be, because the wires are running in the same direction to the left, on the left side of the loop, it will be opposite to that, because wires are running in the currents are running in the opposite direction. And in the other two cases, well, they'll be like this, forces. I'll call this F1, F2, F3, and F4. But F2 and F4 are going to cancel each other. Why? Because they are completely, the magnetic fields are completely the same. The magnetic fields they see are completely the same. But which one is larger, F2 or F3? F2. Why? Because it's much closer to the wire, right? So F2 will win out. So net force would be pulling the wire. So that's good. But let's actually right now be more quantitative and calculate everything. Now, we were given the dependence of the time dependence of the wire's current, which was E to T over tau. Okay. Now, then what's the flux of the loop as a function of time? Well, it's that M I calculated times I wire of T. So it's going to be M I0 e to minus T over tau. What's the electromotive force magnitude for the loop? D flux of the loop dt. So it's going to be M I0, these are constants, T over tau. Because I determined my direction using Lenz's law, I do not care about the sign. I know which way it will be. I just want to give a positive result at the end. M I0 d by dt e to T over tau is minus 1 over tau times e to T over tau. So that's the electromotive force. What's the current? Thankfully, the question actually supplied the total resistance of the loop. So the current will be just epsilon divided by R. So it will be M I0 over R tau e to minus T over tau. Okay? How about part C, the last part? Find the total force the wire applies to the loop. I have already said there are two contributions. Let me quickly do it. I call the first one on the left F1. F1 will be what? Mu 0 I wire times I loop divided by 2 pi. The distance between the left hand side and the wire is D. And I have to multiply this by the side L. F3 would be practically the same thing. Times L, 2 pi. But now, the distance from the wire to the right hand side of the loop is D plus L. Well, that's great. The only thing I need to do is find the net force. It will be F1 minus F3. So mu 0 I wire I loop divided by 2 pi L 1 over D minus 1 over D plus L, or mu 0 I wire I loop over 2 pi. Now I have L, if I just do the algebra, L divided by D plus L here. I know what should be L square, excellent. And I know what I loop and I wire are, mu 0 over 2 pi. I wire is I0 e to minus t over tau. I loop is here m I0 e to minus t over tau divided by tau and r. And then here I have L square D times D plus L. Excellent. So I have mu 0 square. No, that's not mu 0, it's m. It's going to come later. Mu 0 I0 square e to minus t over tau. 2t over tau. L square divided by 2 pi r tau d plus L. Now I have to write also what m was. M I have calculated over here, mu 0 L over 2 pi ln L plus D over D. Good. So mu 0 square I0 square over 2 pi square r tau L cube over D times D plus L ln L plus D over D is the net force. That's usually a scary answer, right? And I know that you guys are bored nowadays. You don't have much to do. Your exam is over, right? So I think it would be nice if you spent 15 or 20 minutes tonight to check if this answer is dimensionally correct. That would teach you a lot about units. And you're taking me seriously, so there is still some hope in the universe. I was trying to joke. I know that nobody is going to do that, but that's okay. Now, okay, let me put aside my attempts at humor. Let's go back and discuss what we were talking about. We were talking about this question. We'll see our exam papers when I finish lecturing, okay? And probably within 20 minutes, so almost at the start of the recitation, okay? But what were we talking about? We were talking about inductance, right? We said if I have, or self-inductance, if I have basically any current loop, there will be some total flux through it. And the voltage and the potential difference across this device would be proportional to the time rate of change of flux. That's Lenz's law. So in other words, potential as a function of time across this device will be d by dt of phi, and phi total will be proportional to the current passing through this inductor, and the proportionality constant was called inductance. All right? So this is going to be L times di dt. Now, what I want to talk about today is what does this inductor, this device, do as a circuit element? Okay. Just like we've talked about the resistor, this is the defining equation for an inductor. So up till now we knew two circuit elements. We knew the resistor, where the voltage current relationship was very easy. V was R times I. We knew the capacitor, where the current voltage relation was what? I was C dV dt, right? The current was basically just time derivative of charge, which was C times V. So now I have my third circuit element, which we call the inductor. Okay. And not quite surprisingly, the circuit element symbol is something that looks like a solenoid. Okay. Good. Now, what can we do with the solenoid? Let's look at what does that formula tell you? L times di dt. It tells you that this element responds to change in current. It basically creates a lot of voltage if you're trying to change the current very fast. So let's do the following. Let's say I take a battery, okay, and tie it to a resistor. And there is a switch here, which I close at t equals to 0. Now, if there is no inductor in the circuit, what would the current running through the system look like as a function of time? Before the switch is closed, current is 0. And after I close the switch, current will start running. What will its value be? V over R. So it will actually just be V over R without the inductor. What happens what do I expect if I actually change the system? I tie an inductor here. What do I expect? I expect the system will not be able to change its current momentarily at a small moment. I expect that there will be some smooth behavior after I close the switch. So let's find out. Let's actually try to calculate the current. So this is no more going to be the case. Let's try to calculate the current in the circuit. So here, let me call the voltage across the resistor VR and voltage across the inductor VL. What does Kirchhoff's loop law tell me? If I go through the loop, potential across the battery must equal the potential drops across the resistor and the inductor. So V must be VR plus VL. Now, in terms of the current in this loop, what's VR? VR is going to be R times I of t. How about VL? VL is going to be L times di dt. So here I have R times I of t plus L times di dt. Now I would like to solve this equation, but what is my boundary condition at the start at time t equals to 0? Is there any current in the circuit? There is no current in the circuit. I have even not closed the switch yet. It's going to be 0. Again, I can use some big words and scare you saying that this is a differential equation we need to solve. But right now you know how to solve almost one, maybe two differential equations. Right? Let me put this in a form that you actually will recognize quite easily. I'll do the following. I'll look at, instead of I of t, I will define a new variable. Let me call that j of t if you want. I'll define it to be minus v over r. I'll look at the difference from v over r. Okay? Now, what would dj dt be? It will be exactly di dt, right? Now, because v and r are constants. So let me rewrite my equation in terms of this new quantity I defined. V will be r times I is j plus v over r times L times dj dt. So now I have v equals r times j plus v plus L dj dt. V is cancelled. So I can maybe write this as dj dt is minus r over L j. Now it looks much easier, right? For which function a derivative results in the same function multiplied by a constant? There is only one function that's doing that, and it's the exponential function. So j of t must be an exponential. Let's plug this value in. What would be dj dt minus alpha times a times e to minus alpha t? So minus alpha a e to minus alpha t would be minus r over L a e to minus alpha t. It's cancelled. Alpha would be r over L. How about a? How do I find a? Let's look at j at time t equals to 0. My definition of j was I of t minus v over r. So I need the current at time t equals to 0. But the current at time t equals to 0 is 0. So at 0 time, j should be minus v over r. Which should be a times e to minus alpha times 0, which is 1. So a is minus v over r. So j of t I found is minus v over r e to minus t divided by L over r. In other words, the current, which is j plus v over r, is minus v over r e to minus t over L over r plus v over r, or it's going to be v over r 1 minus e to minus t over tau. I'll call this, and I'll call tau as L over r. Hey, this kind of is what we expected in the first place, right? So the current is a function of time. Eventually, when time is very large, time is many taus, okay, the exponential factor will be 0, e to minus infinity will be 0. So finally, this curve will reach I over R. But it will not jump to that value. Because of the presence of the inductor, it will go there smoothly. And this curve is pretty much like the charging of a capacitor, right? However, now I have a new time constant. My time constant for the LR circuit is apparently time constant. And here I think I purposefully did not discuss the units of inductance with you. I think this is the right time to discuss the units of inductance. Do you remember what time constant for RC circuit was? Yeah, the unit was that, but the answer was R times C, right? Now, the unit for that is seconds. The unit for R is ohm. The unit for C is farad. So seconds is actually ohm times farad, which is kind of interesting. But that actually makes sense. Think about the definition of R. It's V over I. How about the definition of C? It's Q over V. If I multiply R times C, at least unit-wise, it should be the unit of voltage divided by unit of current, unit of charge divided by unit of voltage, which cancel. But what's the unit of current? Charge per unit time, right? So Q divided by unit of time. So this is seconds. It makes sense. Ohm times farad gives me seconds. Let's again talk about time constant for the RL circuit. What did I say it was? It was L over R. So the unit of resistance is again ohm, but the unit of inductance. What's the unit of inductance? How did I define inductance? I said phi flux is L times I. So what's the unit of flux, magnetic flux? Well, this is B times A, so it must be meter square times Tesla. Unfortunately, I think that's a very unfortunate choice, but even that gets a special name. Meter square times Tesla is called a Weber. All right, so the unit of L will be meter square Tesla divided by ampere. Well, okay, that's nice, but it also gets a special name. It is called a Henry. Okay. Now, when you go to your physics 102 lab, most of the inductors you will find there, all these small solenoids, will have inductances of microhenry, maybe millihenry. So this unit is again like the farad. It's actually a somewhat big, large unit compared to what we have in our labs. But you can, by other tricks, create inductances of the order of tens of Henry, maybe. Now, here's the thing. Is there an easier way to write this unit? Now, what is d phi dt? The unit of d phi dt? Voltage, right? So this should have the units of volt. Which means flux unit divided by time unit. So flux unit, which we called Weber, is actually seconds times volt. Wow, nice. So what is phi divided by I? That's the unit L. So Henry is seconds times volt divided by ampere. But volt divided by ampere is ohm. So that's great. Henry, that's called Henry, but which is equal to ohm times second. So ohms cancel. This is really has tau RL has units of second, just as we expected. Okay. So what does that tell me? It tells me that, first of all, so at t equals to tau, I will actually go to 1 minus 1 over e times v over r of the value. If I wait for, I don't know, t equals 5 taus, I would already reach 90%, more than 90% of my final current. But the larger the inductance, the larger my time constant is. What does that mean? It means it takes more time. If I put in a big inductor there, it's harder to change the current value. Right? Now, here's another thing though. Again, thinking about units. I said from here, apparently instead of farad, I can say seconds divided by ohm, and Henry is ohm times second. So what would be the unit of L times C? The unit of L times C would be, as I said, L is ohm seconds and capacitance farad is seconds divided by ohm. So it will be second square. That's very strange, right? L times C gives you a time unit, well, time square. So square root of L times C would be a time unit. So here is what I'm going to ask next. Let's say that I put an initially charged capacitor of capacitance C and an inductor of inductance L into the same circuit and close the switch at time t equals to 0. What will the current in that system look like? Right? Well, that is something that we are going to find out in our next lecture. But let me give you a spoiler. I know you will not rest until you learn what happens in the circuit. I don't want you to lose sleep over this. First thing you should notice is that if there is no resistance in that circuit, there is nowhere for energy to go. Energy must be either stored in the capacitor here, or somehow it must be transferred to the inductor, which will also store energy. Just like the capacitor, inductor is a device which can store energy by creating magnetic field. But when energy has nowhere to go, it cannot be dissipated, what will it do? It will actually oscillate, go from capacitor to the inductor, and from inductor back to the capacitor. This circuit will be very much like a pendulum swinging. In a pendulum, you either have kinetic energy or you have potential energy. At the start of the pendulum, all the energy is potential, and at the bottom, all of it is kinetic. And here it will be the same thing. The electrons will be either stored on the capacitor or they will be flowing at full speed through the inductor. Okay. So the resulting current will be an oscillating, a cosine function. And here is the interesting thing. The period, well, okay, the period is here. Period of this oscillation will be more or less square root of L times C. Okay, that will actually tell me, that will be the time constant. And pretty much, how do the, okay, that's not entirely correct, but you're freshman, so I can lie to you. Now, how does your phone keep time? How does it count time? Or your electronic watches, how do they count time? They need something which is oscillating every second. And pretty much what they have inside is a circuit like this. There is an inductor and there is a capacitor. The oscillations, they count how many oscillations happen, and that's how they keep track of time. At least some, I think, very, very old electronic circuits did it that way. Now, let's finish today's lecture here, and next week we'll start by analyzing this circuit. All right?